So we continue our discussion. We have discussed that with the Nvidia SXM and AMD OM modules, basically the peer-to-peer memory access will be running faster. Here, the peer-to-peer memory access will be running faster because they don't need to go through the PCIe links anymore. No, they don't need to do that anymore. They are going directly from the GPU to the GPU by going through the NVLink. And the NVLink is designed with higher bandwidth. Okay, that's the benefit. But if we can do peer-to-peer memory access by the NVLink network, then why shouldn't we do message passing between the GPUs by going through the network, the Nvidia NVLink network, or the AMD Infinity Fabric link, so Infinity Fabric network? So the question is, why shouldn't we do that? Well, the answer is very simple. Yes, we can do that. And there is the NICO from Nvidia, which you can use to do the message passing between the GPUs. Now, remember that the GPUs, each GPU, we target to have 1 million threads minimum. If we have 4 GPUs, you are going to have 4 million threads. And these 4 million threads, they need to send and receive message between each other. There's going to be a lot of traffic, right? So we have to understand that. My understanding, the problem of the size. I mean, for 4 GPUs, 4 million threads. If there's 8 GPUs, minimum 8 million threads. This problem of the size is the reason for Nvidia to have this NICO, and also the reason for AMD to have the RICO. We are going to have also RICO from AMD. But the key message here is that with this kind of NVLink network or the AMD Infinity Fabric link, basically you can do message passing between the GPUs. Okay, right now we are talking about message passing between the GPUs intra node. Okay, now let's have a look. What's this NICO and what's this RICO? Okay, NICO is NVIDIA Collective Communication Library, and the RICO is AMD ROCm Communication Collective Memory. And these are the descriptions I have collected from their website. So NVIDIA Collective Communication Library, NICO, is a library providing inter-GPU communication primitives. Okay, the other side, RICO is a standalone library of standard collective communication routines for GPUs. Okay, so what's the, now it's very similar to MPI. What's the communication patterns have been supported by NICO and RICO? We look at these patterns supported by the two, and these are in the color red. So all reduce, or gather, scatter. Well, if you compare the two, they are nearly the same. They are the same, not nearly. They are the same. So mainly are the collective communications, gather, scatter, auto communications. There is right now, I don't see any one-to-one communication here. And in the NVIDIA document, is saying that NICO is not a full-blown parallel programming framework. Rather, it's a library focused on accelerating inter-GPU communications. So that's for GPUs, between GPUs, for the communication between the GPUs. Okay, AMD side is saying it's optimized to achieve high bandwidth on platforms using PCIe and XGMI and networking using InfiniBand verbs or TCP/IP network sockets. So the other side is seeing NICO provides fast collectives over multiple GPUs, both within and across nodes. It supports a variety of interconnect techniques, including PCIe, NVLink, InfiniBand, verbs, and IP sockets. Now, are they the same? Yes. The collective operations are implemented using ring and tree algorithms. Remember the ring and the tree algorithms. We are going to come back to this point later on. And that's a very important message for system architects because you have to take into consideration the ring and the tree algorithm. NICO closely followed the popular collective API defined by MPI. It's very similar to MPI. You can see it's a copy of MPI. Okay. RICO use PCIe and XGMI. XGMI basically is the Infinity Fabric high-speed interconnects for intra-node communication, as well as InfiniBand, RoCE, and TCP/IP for inter-node communications. Okay, so that's the same thing has been mentioned here. This match what has been said here. And the ring and the tree is not mentioned here. It's mentioned is very similar to MPI. And this is basically is saying the same thing. And the supported patterns are the same. Okay. NICO has found great application in deep learning frameworks where the all-reduced collective is heavily used for neural network training. Okay, so these are the extracts from the documents from both Nvidia and AMD. I did this kind of comparison to show you that basically NICO and RICO is nearly the same. It's the same thing. So in the following discussions, we are going to forget about RICO for the moment. We are going to focus on NICO and knowing that RICO from AMD is the same kind of thing. So before diving into the technical details, I mean the implementation details of the NICO, we are going to have a look how the programmers is going to use this NICO communication in their programs. So here comes a program. Just a little bit of mathematics for this piece of code is not so much complicated. The host means the CPU, the server. The server, it has an array, a vector, or a one-dimensional array. In this array, it has the pointers, and this pointer is going to point to a piece of memory located in the GPU. So this is in the CPU. It has a pointer to memory in GPU. And in the GPU, basically, you can understand that you have big array, three-dimensional array with each dimension being 32, 1024, and 1024. So you have this kind of data structure. And then let's have a look how this NICO works. Now, basically, this NICO works very similar as the MPI. Okay, so this we have defined some macros for error handling for the GPUs. This is the starting point of the program. Now we need to know that right now this piece of code is talking about one server. Into this one server, there are 4 GPUs. So one server, 4 GPUs. What we are going to do is that we are going to have a single process, a single thread, or a single thread. We have multiple GPUs. Now, basically, you can understand that you have a sequential code, and this sequential code is going to be executed on a server using a process or thread, and then this process or thread is going to manage 4 GPUs connected to the same server. Okay, so because we have 4 GPUs, we have to have 4 communication objects. So you have this vector with 4 objects. And you have to manage these 4 devices. You have to have some parameters. Number of devices, number of GPUs is 4. Here you have a size, and you have a device. Device basically is a vector, and this vector you have 4 items, 0, 1, 2, 3, and 4. Basically, this is the ID of the 4 GPUs. And then now we are working with the CPU. We are going to allocate a piece of memory to host the pointers. Here, we are going to have two vectors, send vector and receive vector. No, send buffer vector and receive buffer vector. Each vector is going to have the same amount of element of the quantity of GPUs. So if you have 4, you have 0 to 7. If you have 8, you have 0 to 7. If you have 4, you have 0 to 3. So you have these numbers. These are the elements you have for this piece of memory located in the server. And then at the same time, there is another vector S, which holds 4, also 4 elements. Now, we won't dive into these technical details of this S. It doesn't affect our discussion of this kind of communication, NICO communication. So just remember there is an S here. And then what we need to do is that, as I said, that we need to prepare the data. So what we are going to do is that we are going to fill in to initialize the memory. To initialize the memory, so we have 4 GPUs, so we need to work with them one by one. So we do a loop, the for loop from GPU 0 to GPU, for our case, to GPU 3, 0 to 3. We need to do the for loop. So basically this sentence is saying, right now I'm talking with GPU 0. If the first time you go through this line of codes, these lines of codes, is that you are going to say, first I'm going to talk with GPU 0. I'm going to allocate a cooldown malloc, means I'm going to allocate a piece of memory in the GPU. And how much I'm going to locate? I'm going to locate so much elements. Okay, I'm going to have a piece of memory, and I'm going to put this pointer, the pointer of this piece of memory in this vector, and this vector is going to be in CPU. The send buffer is going to be CPU. So I'm going to put it here. I'm going to also have a receive buffer that's vector located in the CPU. It holds the pointer points to the memory in the GPU. So this is the same thing you have twice. First is for send buffer, and then the second time is for receive buffer. Twice time this kind of data structures in your server. And then what I'm going to do is that I'm going to set the values of this array, everything to be 1 for the send buffer. For the receive buffer, everything will be 0. Okay, and then for each GPU, I'm going to create a stream. Now we just pass this stream. Just remember each GPU you need for each GPU you need to have a stream. Okay, and then right now we come to the Nico code. Nico is very similar to with the MPI, as I said earlier. So for MPI, the first thing is that you need to initialize the communication structure. That's the same thing for Nico. You need to initialize the Nico communication structure. Let's say this way, you do the idle check. You are going to call Nico communication initialize, or you are going to have this communication communicators. It has 4 objects, and you are going to tell the Nico you have 4 GPUs, and the 4 GPUs they have their IDs. Here we have these IDs, and here you have the communicator objects for each GPU. Okay, and then the Nico is going to prepare the communication for these 4 GPUs. Okay. Okay, then suppose it has been done successfully. Then what I want to do is that I want to do the communication, the message passing between all these GPUs. What I'm going to calling Nico communication API, because I need to have a group API. Because we have multiple GPUs, so these GPUs then makes a group. So I need to call Nico group start to start a group for the communication, and then I'm going to loop over the GPUs. You have 4 GPUs. That's going to be from 0 to 3. You loop over these 4 GPUs. You are going to tell them, okay, each GPU, please go to these all reduce operations. Okay, for these all reduce operations, your send buffer is here. You give this communicator, and this all reduce function call the pointers to the array in the memory, and then you also give this all reduce functional call the receive buffer, the pointer to the receive buffer in the memory. The buffer is in the GPU memory. You give this functional call the pointer to the receive buffer. The receive buffer is in the GPU memory, and you tell them what's the size of these all reduce operations, and what's the data type, what's the all reduce operation you want to have. Here is the sum, and you have the loop. You loop over the objects. You have 4 GPUs. The first time you call this GPU 0, and then 0, and then you use also the stream 0, etc., and then after you have done the loop, you have called all these 4 GPUs. You are okay. You are going to tell the Nico that the group is end. The group operation has been ended, and then the Nico is going to do what you want them to do. Okay, right now the Nico, the GPU, they are going to work on what you ask them to do, but it takes time. So you need to make sure that the job has been done. Then you are going to, let's say, you are going to read the results. So you need to synchronize on CUDA streams to wait for completion of NICO operations. So here from 0 to 3, first time you are going to talk with GPU 0, and then up to GPU 3, you do the loop 4 times, and you are going to call this CUDA stream synchronize function, and you have 4 streams. You are going to loop over these 4 streams to make sure they are synchronized. Okay, so if these 2 operations has been done without any error message from CPU, that means you are successful. After you have done the job, now you need to free the GPU buffer. The GPU buffer. Okay, you need to free that. If you remember that we want to work with the GPU, we have to prepare everything for the GPU. The GPU, they have lots of computing power, but they are a lot of stupid, so they cannot do a lot of things except the computing, and then you need to help them. So you need to here prepare the memory, the GPU memory. Sorry, you need to prepare the GPU memory, and then you need to free the GPU memory. So from 0 to 3. For the 4 GPUs, first time you are going to set device 0 means I'm talking right now. I'm talking to GPU 0. I'm going to free the send buffer and the receive buffer. The send buffer for GPU 0, the send buffer for GPU 1 up to the 4th. You are going to finish that one, and this is the send buffer. At the same time, you have twice this kind of data structure in your system, and you have to also free the receive buffer. Okay, after you have freed the GPU memory, you can finalize your NICO operation. What do you need to do? You need to destroy the communicators. So you have 1 communicator object per GPU. So you need to destroy all of them. So you need to loop over from 0 to 3 to destroy all these objects, communicator objects. So come back to this NICO functional call, NICO communication message passing. If you are familiar, if you ever read any MPI applications, if you have followed my first section, the computing without any GPUs, I talked about this MPI communication by referring to a piece of example code. If you have read that one, if you have listened that recording, you are going to immediately realize that this NICO functional call, the structure, I mean the code structure is nearly the same. It's nearly the same, and except that for each functional call, you need to use this keyword NICO, means you are working with NICO, not with MPI, because from MPI you also have only this all reduce, and it's going to be confusing for the server, for the CPU. So you have to use this keyword. Except this keyword, that's nearly the same as MPI. That's the reason I have said before that Nvidia, they didn't invent the wheels. They have copied and implemented the basic idea of MPA for this NICO. Okay, so we have gone through this. We have talked about how the programmers, they are going to program the communication between the GPUs, Intra server, using these NICO communication libraries. Later on, we are going to find out that this NICO communication can be extended across the nodes. Basically, on the screen, we have two nodes. The NICO communication, right now, we are talking our code. Our code example has shown a communication, intra-node communication between 4 GPUs. Basically, the NICO communication can be across the nodes. That means if you have 4 GPUs, left-hand side, if you have 4 GPUs, right-hand side, the 8 GPUs can communicate to each other by using NICO. That's going to go across the nodes. We are going to have a look at this one later on, but right now, what we have discussed is a piece of code which is dealing with intra-node GPU communications. Okay. So let's have a rest of 5 minutes. I'm going to stop the recording. After 5 minutes, we are going to come back and continue our discussion. And we are going to have a look of the NICO implementation details. And that's going to be very interesting and challenging. Thank you for your time. See you very soon. Bye-bye.